And I'd like to thank all the organizers for putting on this workshop and giving me this opportunity to present this work. All right, so let's get into it. I'm going to be talking about a system that we called MathCheck, which is based on SAT solvers and computer algebra, which I will go over in a minute. But first, you might be wondering, okay, what's up with this image here, right? This is kind of, what does it have to do with the talk? So the example I'm going to be using to demonstrate our non-existence certificates is from projective geometry. And so this image demonstrates a principle of projective geometry in that, look at the train tracks, right? You can see that they seem to meet. So we know in 3 dimensions, real life, these are lines which will never meet. But when you project them onto the screen, it looks as if they meet at the horizon, right? So in a projective geometry, any 2 lines are going to meet, and this is going to be important. But first, that's a bit of foreshadowing for you. First, what is a SAT solver, right? So when I say SAT, it's short for satisfiability. Satisfiability, this is a classic problem from logic and computer science, where you're given a logical expression and you're asked to make that expression true. Can you come up with an explicit assignment to the variables which makes the expression true? All right, if you can, and then you are said to satisfy the formula. Now, surprisingly, SAT solvers are pieces of software which are going to actually solve this very effectively in practice. It's absolutely astonishing when they work well. They work really well. And in fact, so well that people will have problems which have nothing to do with logic. They will go to the trouble of translating their problem into logic just to run a SAT solver on it, because SAT solvers are that good. They are the best way to solve their problem, which has nothing to do with logic. An example of this is from hardware or software verification or discrete optimization. So on the right here, an example of this, I have a chessboard where I put a queen in every square. And we want to color the queens so that queens which could attack each other are colored differently. All right, the question is, what's the minimum number of colors necessary? So this is an optimization problem. You encode this into logic, run a SAT solver on it. The SAT solver almost immediately will come up with this coloring. It's a 9 coloring. But more interestingly for this talk is that it will also produce a certificate of non-existence for the 8 coloring. There is no 8 coloring that exists. The SAT solver will not only tell you that, it will provide you with a proof that can then be verified. So we're going to be using that functionality. The other piece of software I want to talk about is CAS, or computer algebra system. These are software which does they're designed to do mathematics and high-level mathematics, right? You can give them graphs, you can give them matrices, or then you can compute with groups. For example, here I have this 8 vertex graph. You can ask a computer algebra system to give you the set of the automorphism group and a set of generators, for example. Right, and then you can do computations in that group. So CAS are really good at designed to do mathematics very effectively. Now, this brings me to the SAT plus CAS paradigm, because there's a lot of problems where you want both really good search routines and really good mathematical routines, right? The SAT problem is inherently a search problem. You're trying to find this satisfying assignment in an exponentially large space of possible assignments. SAT solvers are great at search, but they're not so good at math. Whereas computer algebra systems are great at math and not so good at search. And so this was the motivation behind MathCheck. And we've used it to look for lots of different types of combinatorial objects. I've shown you on the slide here a Hadamard matrix, which I've color coded to show you the structure. You know, obviously this is a very interesting type of matrix. I won't get into that, but you can check online for the papers. The other thing I want to talk about is on the other side, if you look for an object and you can't find it, right? You don't just want to say, okay, well, we couldn't find it. We want to produce a proof that it doesn't exist. So MathCheck can also produce non-existence certificates, which brings me to projective geometry, as I mentioned. And I love this topic because it has a really rich history and it's very visual. And so the interesting history is that, okay, so we all know Euclid, right? Euclid was the inventor of geometry. He defined the postulates or the axioms which characterize geometry. At least everyone believed this for 2,000 years. The interesting thing was his last postulate, this parallel postulate, was more complicated than his other postulates. And so mathematicians were kind of bothered by this. They wanted to prove the parallel postulate in terms of the other postulates. And they tried to do this for 2,000 years, and it turned out it was impossible. Right? In the 1800s, it was noticed that there are other models of geometry where the parallel postulate will fail, For example, in projective geometry, you have this projective axiom which says parallel lines don't exist. Any two lines are going to meet at a unique point, all right? And furthermore, in the 1800s, it was also noticed that not only are there alternative models of geometry, there are also models that only have a finite number of points. The really interesting thing in finite geometry is that all finite geometries have been characterized, except for those in exactly 2 dimensions. These are the projective planes. So lots of work has been done on trying to find which projective planes exist. How do we characterize or classify these objects? Here's an example of one for you. This is called the projective plane of order 2. It's the order n, a projective plane is order n if every line contains n plus 1 points. So here, indeed, every line here contains 3 points. This is easy to verify. I've color-coded the lines and points so you can look at it and verify for yourself that all the axioms are satisfied, right? If you take any 2 lines, they intersect in a unique point. This is kind of a restrictive condition. And, okay, so I have to clarify one thing perhaps. Some of you might be thinking, okay, well, what's up with this circle here, right? It's like you said you had lines, and I can see 6 lines in a circle, so what gives, right? I think you cheated when you drew this diagram. So when you're working axiomatically, you don't want to have your biases of what you think a line is, influence what the axioms are actually saying a line is. So the axioms just say if you have 2 lines, they intersect at a point. They don't say how you represent those lines, right? If I want to draw it like a circle, well, I can, as long as I satisfy the axioms. So in fact, you can actually go a bit more complicated. Here's a projective plane of order 3. There's 4 lines on 4 points on every line. All right, so these things do exist. And the interesting thing is the first open case, at least theoretically, is at 10, right? This is known as Lamb's problem, to try to resolve, either find a projective plane of order 10 or prove it doesn't exist. This was a very famous problem for a long time. Lots of people worked on it. Here's one quote from Urbach in 1976. And this is where he brought up, okay, well, these ovals should be an important subcase to try to resolve this Lamb's problem. And so what is an oval? An oval is just a set of points where no 3 points in the oval lie on the same line, right? It's also going to be of largest possible size. This is either n plus 1 or n plus 2 points, depending on the parity of n. But the interesting thing is that all known projective planes contain ovals. And indeed, I've shown you 2 projective planes here, and I've highlighted an oval in each of them. All right, so we have, you can verify again for yourself that yes, no 3 points lie in a single line in either of these ovals. All right, so this is the statement of the problem to try to find, if all projective planes that we know of contain ovals, what if the projective plane of order 10, assuming it exists, does it contain an oval? This was actually first shown to be false in 1983 by the team that you can see here. Lamb and his collaborators wrote a computer program which then verified the non-existence of ovals. All right, and you can see them looking at, I believe, like a tape drive containing their code and pages and pages of computer printouts. This was a massive search, and they were upfront about what it entailed. Right, they wrote custom written software that was run once on a single piece of hardware, and there was no certificates of the search produced. You just have to simply trust that it ran to completion. And so they also mentioned that, it's very easy when you're writing software which is only going to be run once, it's specially written, it's very easy to make a bug, especially when you're trying to make it run fast. So they requested independent verification because of these limitations. And as far as I know, this had never actually been done in the last 40 years. Until now, we actually have gone a step further and provided a set of non-existence certificates for this non-existence of ovals. So the upshot now is that any third party can check the certificates for themselves, and once they believe in the encoding, they don't have to trust search code that they can't even, the search code isn't even available in LAMP search. So now you don't have to trust a search algorithm. You can just run a proof verifier on these certificates. So how are we going to, as I mentioned, we're going to use a SAT solver. How are we going to reduce the problem into SAT? So first of all, we use the standard concept of an incidence matrix. This is just encodes which points lie on which lines, right? We're not actually going to use those nice colorful diagrams when we're doing structuring the search. we have a 0, 1 matrix. The 1 in the ijth entry is going to denote that the ith line contains the jth point. So the rows contain, or they signify the lines. The points are signified by the columns. And the SAT encoding is very nice because since this is just 0, 1 matrix, every entry just gets its own variable, right? When we're encoding this into Boolean logic, false variables will denote a 0, true variables will denote a 1. And we can start filling in some entries in this projective plane. So we know that if the oval exists, it's going to contain exactly 12 points. And we can assume without loss of generality, that's going to be the first 12 points in the oval, right? Every point is equivalent at this stage. Furthermore, we know there's going to be exactly 66 lines through the oval because any pair of points in the oval will define a unique line, right? So there's 66 lines. And so this is the incidence matrix as it starts out. So we have 66 lines. Those are the rows. We have 111 columns. Those are going to be the points. And the points of the oval are the first 12 columns. And so you can lexicographically order the lines so that we get this nice pattern here. All right, so the question is, okay, how do we start filling in more entries, right? The gray entries are unknown. So we know there's going to be, in a projective plane of order 10, there's going to be 11 points on every line. So we can start filling in some entries here. We already have 2 points on the first line. And that means there's going to be another 9 points. And so these 9 points will just be assumed to become first, right? Without loss of generality, we just put them there. And then underneath them, we have a block of zeros because in the projective plane, any 2 lines intersect exactly once, right? And if you look at the lines 2 to 21, they already intersect the first line in the oval itself. So they're not going to intersect the first line again, and so we put zeros here. You can repeat this reasoning over again multiple times, and you get a structure that looks like this, right? In fact, you can go a bit farther and start filling in more entries, but I'm just going to stop here. This gives you a nice picture of what the incidence matrix looks like, all right? The really interesting thing is how do we encode the axioms into SAT? So sometimes you have to be a bit clever about this because Boolean logic is a very weak logic, right? All the variables are either true or false. Sometimes you have to be a bit tricky about how you go about encoding these properties. And so indeed, if we're going to say any 2 lines meet exactly once, we're going to say any 2 lines meet at most once, and any 2 lines meet at least once. All right, so I'm going to give you 2 examples of those just to give you a taste of what these conditions are going to look like. So, all right, so I've highlighted 2 lines for you here, and we want to say that these 2 lines meet at most once. All right, I have 4 points A, B, C, D, these 4 entries which lie on the lines. We know that they can't all be true because if A, B, C, D were all true, then these 2 lines would intersect twice. All right, so they can't all be true. This is, in Boolean logic, you encode it in this format at the bottom. So this is notation that logicians like to use. It's just saying at least one of A, B, C, and D is false. All right, in technical terms, this is known as a logical clause. And this is how you communicate with a SAT solver. You just come up with facts that you know about the search space. You don't have to write any search code yourself. You're telling the SAT solver or declaring the facts that you know. The other example I want to show is just, okay, say we have the first line and this line here, and we want to encode the fact that they intersect at least once. Then if they're going to intersect, they have to intersect in these columns here because after the words, there's just a bunch of zeros on the first line. All right, so they have to intersect somewhere between A and I. So if they are to intersect, at least one of A to I must be true. And again, at the bottom, this is a Boolean logic clause. You just provide this to the SAT solver along with many other clauses of this form so that you just give the SAT solver everything you know, then the SAT solver is going to do this search. In fact, we're only going to use the entries in this submatrix that I've shown here. This is just to cut down on the search space. You can use the whole matrix, but this is a bit excessive. There's more clauses than necessary that the SAT solver has to keep track of, so it tends to slow things down. So in fact, this submatrix will be sufficient. And just to give you a taste of the size of this search. This is an enormous search. So I've split it up into 5 blocks here, signifying by the orange rectangles, and each block has over 10 to the 14 possible ways of filling in the entries, the gray entries, in a consistent manner. So it's just an enormous search. But immediately, one way to cut down the search is to note we can actually, everything's equivalent up to permutation of row and columns. And if you remove those equivalences or symmetries, there's only 396 ways of filling in the entries in the first block up to equivalence. All right, so that goes from 10 to the 14 down to 396, right? This is an enormous reduction in the search space. Furthermore, you can actually compute with what case you're in using a CAS or a symbolic computation library. We use this library called Naughty. And the idea is, given an explicit 0-1 matrix, a completion of one of the blocks, Naughty can tell you which case you're in, right? It'll be, we can assume we're going to get a tag between 1 and 396. All right, so every block can be given a tag. And the other property that we can assume is that since the blocks are basically all equivalent, they can be permuted freely, we can assume the first block's tag is minimal. All right, so this is actually going to be a significant reduction if we can come up with a way of encoding it into logic. And so this is what I'm going to mention now. We use this learning method. And so this is the interface between Naughty and the SAT solver. The SAT solver is going to be looking for completions of the blocks, right? We gave it the submatrix and said, okay, try to find an explicit completion. Say it finds the completion of the second block, B2. We take the second block, we give it to Naughty. We have Naughty compute the tag of the second block, which case it's equivalent to. If the tag of the second block is smaller than the tag of the first block, this is going to violate the criterion we assume that the first block's tag was smallest. Therefore, we can learn a clause which is going to block it. So we just say, ignore this from the search space from now on, try something else. In technical terms, it's called a symmetry blocking clause, but in any case, it's learned, and the SAT solver is going to use that fact to cut down on the search space. And indeed, here's a graph of the running times plotted against the first block's tag. And as you can see, as the tag of the first block is increasing, the running time is decreasing significantly, right? Because we're learning more and more of these symmetry blocking clauses. And this is significantly cutting down the search. So the running times are going from about half a day to a couple of minutes. So it was a very effective method once you get it working. And in fact, we did actually find some completions. So here is one particular 5-block completion of that submatrix. We found 58 of them in total. And the thing is that at this stage, the search space is so highly constrained, you can easily show that these can't be extended to a 6th block, right? This is just, this is as far as you can go. After this, so this is a proof that ovals don't exist because you can't extend these matrices any further. So the certificates, as I mentioned, are generated as the SAT solver is solving these SAT instances. They are of a significant size. They're about 3 terabytes in total. But the upshot is once you have those certificates, now you don't have to trust any special purpose code, right? The things you have to trust are, first of all, the SAT encoding, right? This is pretty straightforward. I already outlined it for you. You also have to trust the generation script for the SAT encoding. And then the proof verifier drat trim. This is a standard proof verifier from the SAT community. There's lots of them. You can run it on other proof verifiers. And then the most significant amount of trust, I would say, is the symmetry blocking clauses, which rely on the correctness of Naughty. So Naughty is a well-tested piece of software. However, it is fairly complicated. So this is the, you have to trust that the results that were coming back from Naughty are actually correct as well. But once you trust those, you just have to run the proof checker on the certificates. So in fact, this is only one case that I've outlined of Lamb's problem. We do in fact now have a complete verification of Lamb's problem. We've solved the other cases that are necessary. Some of this work has been published. You can see these 2 papers here, and the full resolution should be, look for that soon. But just to sum up the work, So I've outlined the SAT plus CAS paradigm, right? This is an effective way of searching for combinatorial objects or disproving their existence, as we've seen. And I want to stress it does have very wide application, right? There's lots of mathematical problems, as you all know, where you really want fast, powerful, and verifiable search tools. And the SAT plus CAS method hits all three boxes there. And it gives you good bang for your buck. Yes, you do have to know some knowledge of SAT solvers and CAS, but yes, you do have to encode your problem into SAT. This is a different way of probably thinking about the problem than you're used to. But the upshot is if you're able to do this reduction, it allows you to avoid writing special purpose code, which, as I've mentioned, is a very error-prone process, and it's difficult to make your searches very efficient, right? Whereas a SAT solver already has decades of work gone into making it run very efficiently, right? It's actually going to be very difficult to beat a SAT solver at doing search unless you spend a lot of time optimizing your search algorithm. So also, the benefit is you don't even have to trust the SAT solver, right? It's hard to trust special purpose search code. SAT solvers are well tested, and you don't even have to trust them in the end because they provide you with a proof certificate, which then can then be verified. The downside of using SAT is that you lose the mathematical functionality that you might want to use, but this is where the CAS comes into play. If you can link up the SAT solver to the CAS, you can then query it to learn facts and then thereby get the best of both worlds. So thank you. I'll stop there and be happy to take any questions.